right, so today we're actually going to talk about computation of homology and persistent homology, and we're going to go through small examples. But before I do that, I have some comments from a last lecture. Since at the last lecture we talked about the mapper algorithm, right? So there's a lot of different directions that it's a very actively researched area, and there is different variations of the mapper. One of them is called multi-scale mapper. And the idea of multi-scale mapper is that there is some sort of inclusion over the cover element. So let's say I have, remember I have, let's say a simple shape, which is a circle or a torus. I can have a cover element that is 2 elements, right? But I can also have a cover element that maybe there's, 4 of them. I can also have, in some sense, 8 of them. Okay, the way I'm roughly drawing here is you could imagine that there is some sort of inclusion over the cover element. So you start with 2 and then 4, then 8 and so on. So there's a nice inclusion over how the cover element is constructed that induces some sort of inclusion between the mapper object that you are constructing. And when they talk about multi-scale mapper, it's instead of having one single, say, mapper graph, you are looking at a sequence of mapper graphs. And then that is the object you're going to study. Okay, so that's one variation of it. There's also the really big question of automatic parameter tooling. And there has been some progress in that direction. And then the rough idea is, again, mentioned from last semester, is that you could potentially, look at, as I'm changing my parameter, how much does my topology change? For example, like in this case, if I just have 2 cover element, then my mapper object is looking like this. Otherwise, it's going to look like this, or it's going to look like, like this. Meaning that as I'm kind of, changing my cover, that all of a sudden I go from having a loop or not having a loop to having a loop. So one of those guidelines in trying to find automatic parameter tooling is, can I find this transitional point where there is observable topological changes to my summary? And maybe that will be the range of parameter that I care about. Okay, so there's still active research. And the last part is the theoretical understanding of both going from 1 dimension to 2 dimensional to high dimensional. When I say high dimensional, I'm really saying that my function is from some topological space to R of k. Let's say k is bigger or equal to 3 or 2. Well, let's say 2. Okay, so this is what I would call multivariate scenario. And then because remember, there's a relation between the mapper graph and then the REAP graph. So if you go back to the picture of the REAP graph at the beginning, right? In this case, remember the REAP graph is shrinking every single level set or the contour at a particular value right here to be a component, and you get like the nice topological summary of the entire space. Mapper instead of looking at a particular value and the inverse map of the value, is looking at the interval and the inverse map of that interval. So in some sense, the mapper graph, as we described it, is approximation of the REAP graph. So there's always a question about approximation quality. In some sense, is that as I increase my number of cover element, right? As I increase, for example, if I increase my number of cover element and I decrease maybe the size of the cover, size of the interval, how fast and is my mapper graph converging to the REAP graph? So that is also a theoretical question to ask. And another theoretical question to ask is that, you have my ideal space, which is this circle, for example. In practice, you only have a sample of that space. So depending on your sample quality, you can, can I use my sample quality as a parameter to understand how well my mapper graph is approximating the ideal sort of REAP graph? So in terms of theoretical understanding, there is always the question of what is sort of the limit theory right? What if I am going to infinity over my sample, or if I go to infinity over my cover element, how fast and is my approximation to the RIP graph approximating the RIP graph, and the approximation is the mapper graph. So there's a lot of active research in this area that is surrounding the theoretical understanding of this object. But in practice, it works pretty well for, for a lot of different applications. Okay, all right. Okay, any questions over mapper before we move on to homology, which is really pretty, then I'm going to move to that. Okay, I'm a little bit behind over my lecture number, but I'm still covering the right amount of content, so we'll just take our time. So today we're going to move on to, well, lecture 7, which is on homology and computation. And before I go into the detail, I have to give you a warning, is that things that described in today's lecture is pretty much a chapter in algebraic topology book. Okay, so if you're unfamiliar with it, feel free to interrupt me, because it's going to be very dense. Today is a very dense lecture. It's a very dense mathematical lecture. Okay, so the idea of a homology. So remember, we talk about complexes, simplicial complexes. Okay, so let me just do a quick review of simplicial complex before we forget. Remember, a 0 simplex is a vertex. A 1 simplex is an edge. A 2 simplex is a triangle. And a 3 simplex is a tetrahedra. And remember, they are solid, okay? It's included in its interior. If you recall earlier lecture, when we, in order to understand sensor network, we have to introduce this concept. And the technical definition is a k-dimensional simplex is sort of the convex hull of k+1 vertices. Okay, so that is the technical definition, but it's easier to understand this way. Now, if I have a simplicial complex and P is a dimension, there's this concept called chain complex. Okay, but before I do the chain complex, I need to introduce the coefficient. So the coefficient is what's called Z2 coefficient. So Z mathematically means integer. Z2 is really just a notation to say that I only have 0, 1 as my set. Okay, so all that means is that I'm going to do some operation, and the coefficient I care about is either 0 or 1. Okay, so it's like a sort of binary coefficient. So that's the first thing you need to get familiar with. And this is what we call modular 2 coefficient. But all you can think about, this is really the things when you say modular 2, right? All my operation is sort of binary operation. What does that mean? Is 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, and 1 plus 1 is equal to 0, because I'm always taking modular of 2. Okay, so those are the operations. Now, what is a p-dimensional chain? Okay, so first of all, what is p? In this case, in this example I'm showing here, p can be 0, p can be 1, or p can be 2. So this is the dimension of the simplices I care about. And p chain is a formal sum of p simplices. What do I mean by that? It's a linear combination. A 0 chain is a linear combination of vertices, of 0 simplices. A 1 chain is a linear combination of 1 simplices, and 2 chain is a linear combination of 2 simplices. And this is algebraic topology, meaning that I'm going to do algebraic operation. Okay, so let's look at this. First of all, the picture I'm drawing is a simplicial complex. Okay, this simplicial complex has 4 vertices. 1, 2, 3, 4. Those are 4 vertices. It has 5 edges. 1, 2, 2, 4, 1, 3, 2, 3, 3, 4. It has 1 triangle. So that's 1, 2, 3. All right. So now, remember I said, I'm going to ask you, give me an example of a 0 chain. Okay, what is the example of a 0 chain? Remember my definition. 0 chain is a linear combination of vertices. So a 0 chain can be, let me just use C as chain. 1 0 chain is going to be 1 plus 2 plus 3. That is my linear zero chain. It's a linear combination. And because I'm using 0, 1 coefficient, I'm going to ignore the 0 coefficient. Really, I can say it's, this is 1 plus 2 plus 3 plus 0 times 4, meaning that I don't include 4. Okay, but I'm going to ignore anything with a 0 coefficient. So I'm only care about 1 coefficient right now. So a 0 chain can be 1 plus 2 plus 3. It can be a single vertex, 1. Or it can be, all the vertices, 1 plus 2 plus 3 plus 4. So this is a bunch of linear combinations. And one chain is linear combination of 1 simplices. So what is a 1 chain? For example, 1, 2 plus 2, 4 is a 1 chain, right? It's just a linear combination. Literally thinking about this as like algebraic operations. Okay, so that is what we call 0 chain, 1 chain. And of course, 2 chain. What is a 2 chain? A 2 chain is 1, 2, 3, because linear combination of all the triangles. I have 1 triangle, so I can have 1 times this triangle. That's it. Okay. Again, feel free to interrupt me because we're going to go from there here. So, okay, I just give a bunch of examples in the previous thing. Let me repeat it again. I'm going to use C0 for an example of a 0 chain. So 1 plus 2 plus 3, a linear combination of vertices is a 0 chain. 1, 2 is edge 1, 2 plus edge 2, 3 plus edge 3, 4 plus edge 2, 4 is a 1-dimensional chain. A 2 chain is linear combination of triangles. So 1, 2, oh, I made a mistake. It should be 1, 2, 3 because 1, 2, 4 is not a triangle. Did I do it right? Yes, this should be 1, 2, 3. Okay, so now because of the chain, I can compute addition of the chains. All right, so let's say I have 2 chains. One is 1 plus 2 plus 3. This is a 0-dimensional chain. I have another 0-dimensional chain, so I can add them together. Okay, so let's say I'm going to C0 is 1 plus 2 plus 3. C0 prime is 1 plus 3 plus 4. I'm going to add those 2 things together. So C0, actually this is another typo, sorry. C0 plus C0 prime is 1 plus 3 plus 1 plus 2 plus 3 plus 1 plus 3 plus 4. So what do I have? I have a 2 copy of 3. But remember, 1 plus 1 is equal to 0. So pretty much they cancel. Okay? And I have 2 copies of 1. Again, 2 copies, 1 plus 1 is 0 in my Z2 coefficient. They cancel out. So what I get is 2 plus 4. All right. So this is all pretty. As you will see very soon, this is all operation within a group. But anyway, so let's say once I have those chain, I can do linear combination. Okay. So the mathematical formulation is to say, okay, if my first chain having a coefficient, AI, the second chain has a coefficient BI for a particular element in my chain, then when I add, I just add the coefficient. But when I add the coefficient, remember, I still have the operation 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is 0. Okay, it's all mod 2 coefficient. All right, so everything I'm describing today, when I compute homology, I'm using Z2 as a coefficient. But in practice, you don't have to be Z2. It can be field, it can be real numbers, and so on and so forth. But for simplicity, pretty much throughout the semester, we're going to talk about Z2 coefficient because it's most easily understood one. Okay. So now I can do operations, basically additions of those chains, right? I mean, let's do an example for edge. So let's say I have a 1 chain, which is 1, 2 plus 1, 3, and another chain C1 prime, which is 1, 2 plus 1, 3 plus 3, 4. Again, if I add those 2 chains together, C1 plus C1 prime, I have 2 copies. All the 2 copies cancel out. I'm going to get the edge 3, 4. Okay. All right. So once you understand what is a chain and how do I operate on chain, I need to talk about something called a chain group. But now this is the part you may or may not have seen. This is again in actually standard linear algebra. is the idea of group and abelian group, okay? So again, feel free to interrupt me if you think this is going too fast. So what is a group, okay? A group is a set, okay, with some sort of operation, okay? I'm using dot as operation. So, and it satisfies 4 conditions. The first condition is called closure condition. If I have 2 elements in this group, then A and B in this group, then A operate with B over this operation is part of this group. So it's much easier for me to give examples of it. So let's say my example of a group is a set of integer together with operation that is addition, okay? So let's check this is a group. Z corresponding to the set of integer. So let's say it's, you know, -2, -1, 0, 1, 2, 3, and so on and so forth. That is my set. That is my set. It's an infinite set. And my binary operation is addition, okay? So now let's check this is a group. Whenever there's 2 numbers in this set of integers, their addition is also integer, okay? That's the first closure property. Associativity is to say A plus B plus C, where I do A plus B first and then plus C, is going to be equal to A plus B plus C, where I do the operation between B and C first, right? So essentially 1 plus 2 plus 3 is equal to 1 plus 2 plus 3. So associativity, okay? That's easily satisfied. Identity element, it says that there exists some element such that if I operate on this identity element E, I'm getting back myself. So what is identity element for the set of integers under plus operation?
0. 0.
Exactly. 0 is my identity, right? Because 2 plus 0 is equal to 0 plus 2, which is 2. Exactly. So now the inverse element is for any element in my set, there exists an element such that when they operate on each other, so in this case, addition is equal to my identity element. So if I have an element A in my set, where A is an integer, what is its inverse?
Negative A.
What's that?
Negative A.
Exactly, right? Because A plus negative A is equal to 0. So now I have checked to see all those 4 properties satisfied. So the integer, the set of integer with add operation is a group, okay? So, of course, you can check this is also a group. This is much easier. Remember, Z2 is just 2 integers, 0, 1, okay? And I'm going to see this with addition is also integer, right? But of course, my addition, this is Z2 coefficient, so my addition operation has to be a little bit special. It's to say, okay, 0 and 1 is in this group, then the addition 0 plus 1, 0 plus 0, 0, 1 plus 1 is always in this group. But remember, 1 plus 1 is always equal to 0. So that is satisfied. And then there's also associativity. You can check the identity, inverse, and so on and so forth. So what specifically in this case, what is the inverse of 1? For this group, what is the inverse of number 1? What is its inverse?
1 itself.
What's that?
0, because 0 plus 1 will be 1.
Inverse. So in this, first of all, let's ask this, what is the identity in this set? What is the identity element?
0.
Yeah, 0 is identity, right? Because anything plus 0 is equal to itself. However, the inverse of the element 1 is 1, because 1 plus 1 is equal to 0. Okay? All right, so now this is a definition of a group. Group satisfies those 4 conditions. Or you can also check other type of groups. For example, ask yourself, is my is my R real number plus addition operation? Is that a group? And so on. Okay, so this is a question for you to double check. And also, like, if my integer versus multiplication, is that a group? Okay, you want to ask yourself. Okay. Now there's an additional requirement of abelian group. Abelian group asks for one more thing, which is commutativity, which is A operator on B is equal to B operator on A. Okay. So of course, if you think about the set of integer with add operation, it's abelian also is because A plus B is equal to B plus A. So you can switch it and then your result is the same. And same thing with Z2 plus, this is an abelian group. Okay. So now there's group and then there's abelian group. So now let's get back to my chain. Remember my chains are linear combination of vertices, linear combination of edges, linear combination of triangles, and so on. So a p-dimensional chain where p is equal to 0, 1, 2, and so on, together with the addition operation I just described, is a group, okay? Because you need to check all those 4 properties. Okay, so remember what I need to check? I need to check, let's say now G is my group of chains. I want to say if I have 2 chains, if I add them together, the end result is also a chain. So that's a closure. And also associativity is dependent on the ordering, how my chains are added, it's equal. Identity is that is there exists an element, which is when I add to the chain that it's equal to the chain itself. And then finally, does there exist an inverse of my chain? Okay, so all this you have to check, but let's see, basically, remember what I'm going to say is capital C of 0 is a chain group where it's a set of chains where the operation on additions. And this chain group is all the elements are linear operations of vertices, or sorry, a linear combination, which is what I call sums in the slides. C1 is all the chains that is linear combination of edges. And C2 is all the combination where elements are sum of triangles. Okay. So let's first check that any chain, like I said, if I just focus on p-dimensional chain group, so it's p-dimensional thing. Let's, for the time being, if you assume p is equal to 0, that's much easier to understand. The first part is to say, when I have 2 chains, I add them together. If I have 2 chains in my group, their addition is in this group. If I have 3 chains, the ordering is commutative. So that's the second property I want to check. The third one is there's always a 0 chain operation where if I add to it, it's equal to, a typo, the chain itself. And the last bit is it always has the inverse. And in this case, the inverse of a chain is always itself, because if a chain added to itself, because I have Z2 coefficient, they cancel out completely. So the inverse of a chain in this case is always 0. Also, it always itself. And finally, if I switch the order of how they operate, they're always the same. So in some sense, not only it's a group, it's also a abelian group. All right. So let's get back to our example. Okay. So let's give a very concrete example as this one before. I have 1, 2, 3, and I have 4. This is my simplicial complex. Actually, let me just do it exactly the same. So now, or actually, let me just do it in a new slide. Okay, this is my example. Now I'm going to list the element in my 0-dimensional chain group. The elements are, remember, they have to be linear combination of vertices. So a single vertex is a linear combination of a single vertex. So every single vertex is in the 0-dimensional chain group. And then any 2 of them is a linear, is part of the 0-dimensional chain group. Any 3 of them add together okay, I did not enumerate all of them. And then of course, the last one is all 4 of them add together is part of 0-dimensional chain group. Okay. Same thing with C1, single edge is part of the one chain. 2 edges add together is part of the one chain. 3 of them add together, and 4 of them add together, and 5 of them add together. That's all part of the one chain group. Okay. And then, of course, in this case, the only element in my, well, it has to have a 0 element. So let's see. Linear combination of my 0. So let me put 0 elements in there just to be sure, because you always have an empty chain. Okay. So those are, let's check, let's say I want to check that this is indeed a abelian group, right? So you know that if I take 2 elements, let's say 1 and 2 is part of C0. This is just a valid verification. We know that 1 plus 2 is also part of this. So we have this sort of closure property, okay? And now if I do, I know 1 plus 2 plus 4 is equal to 1 plus 2 plus 4. That's fine. So that's the second property, commutative property. And then since 0 element is there, 0 plus the chain 1 plus 2 plus 3 is equal to the chain itself. And then the last, for the group, if I have 1 plus 2 plus, let's say 1 plus 3 plus 4, 0 chain add to itself, this is equal to 0 because all the 2 coefficient is zeroed out. And finally, I want to say it's abelian because I want to say 1 plus 2 plus 1 plus 3 is equal to 1 plus 3 plus 1 plus 2. I just order the shift of the chains, okay? So you can do this check. So you know that the collection of all the linear combination of vertices form my 0 chain group. The collection of all the linear combination of edges is my 1 chain group, and so on. All right? Any questions so far?
There's a question in the chat. For 1 chains, does the order of numbers...
I couldn't hear you, Faye.
Can you hear me now? Hello?
Your volume is very low.
Can you hear me now? Is it working?
Barely. Can you say what's your question?
Can you hear me now?
Yes.
Okay. So there's a question in the chat. For 1 chains, does the order of numbers matter? Would 1, 2 be the same as 2, 1?
Yeah, the order doesn't matter actually. Linear combination 1, 2 plus 3, 4 is exactly same chain as 3, 4 plus 1, 2. This is one single chain.
So is 1, 2 the same as 2, 1?
Oh yeah, 1, 2 is the same as 2, 1. Yeah, so 1, 2, yeah. It's just represent that edge. Okay. All right, so I'm going to describe boundary, but we are just exactly at the breaking point. I'll give everybody a 5 minutes break. I think, you know, you can think about what does this mean, right? Is that I have elements from my simplex and I can operate on them. So, okay, so 5 minutes break and we'll be back. And feel free to ask questions during the break too. Okay. All right, let's resume. Let me add an additional comments because one of the question is, does the order matter? In our situation, actually, also throughout the semester, we assume our simplicial complex is not directed, but you could imagine I have directed simplicial complex, meaning that I have some sort of orientation that is attached to the simplex. So for example, I can have an arrow for all the, let me draw it larger. I can have an arrow for each of the edge, and I can also orient the triangles too, right? But if you do that, then the edge 1, 2 is not equal to the edge 2, 1, assuming that I'm going from edge 1, 2 goes from this direction, edge 2, 1 goes from this direction. But we're not dealing with directed cases. So for all our examples, that the direction doesn't matter. Okay. All right. So now let's move on. Once you have a simplex, there's an operation called the boundary of a simplex. And then the boundary of a simplex is the sum of its p-1 faces. Okay, so remember a face. So if I have a simplex that is a linear combination of those vertices, a face of it is a linear combination by omitting one of the vertex. In this case, this is really the p1 minus 1 dimensional face. So what is happening is that the boundary is a linear combination of all these faces. So let's say a simple example. Let me just give one single simplex. Let's say my simplex sigma is equal to linear the 1, 2, 3, right? I kind of have used other notations 1, 2, 3 to say it's a triangle. But now I'm going to use this notation just to emphasize what it means when I take the p-1 face. So this is a 2 simplex, okay? And then when I say it's a face, what is a face? One face of sigma is 1, 2, 3, but omitting the vertex 1, which is the edge 2, 3. And then omitting the vertex 2, which is the edge 1, 3. And then omitting the vertex 3, which is edge 1, 2. Okay, so this hat operation is just say getting rid of it. So now if I take the boundary of the sigma, if I take the boundary of this operation, so this is my boundary operator of this simplex, this is a linear combination of all its faces. So it's equal to 2, 3 plus 1, 3 plus 1, 2. Okay, but if I simplify it, really it's saying that the boundary of the triangle 1, 2, 3 is its edges 2, 3 plus 1, 3 plus 1, 2. Okay, and then from sort of intuitive way of understanding it, if you take a triangle, what's its boundary? Its boundary, literally in English meaning, it's all the edges that surround it. That's its boundary, right? So in this case, the boundary of a triangle, it's all the edges, okay? But of course, when you operate on a simplex, you can also operate on a linear combination of the simplexes. So you can define what's called the boundary of a chain. So now in this case, my chain is a linear combination of edges. Oh, first of all, let's do a boundary of a single edge. The boundary of a single edge, right, is going to be, let's say I'm going to do 1, 2, but removing 1 plus 2, 1, 2, but removing 2, which is equal to 2 plus 1. So the boundary of an edge 1, 2 is its vertices. Not surprising because if you imagine 1, 2 is my edge, then the boundary it's vertices. Well, it's literally on the boundary of it. Same thing with the previous picture. If I have my triangle 1, 2, 3, then the boundary of it, it's all these 3 edges. Okay. Now, if I operate over a linear combination of simplexes, for example, in this case, this is a linear combination of edges, then I can do the boundary of this chain, which is a boundary of this linear combination, which is operating on the boundary on each of individual element. And each individual element is an edge. The boundary of an edge is its vertices. Right? So the boundary of 1, 2 is 1 plus 2. Boundary of 2, 3 is 2 plus 3. Boundary of 3, 4 is 3 plus 4. And I add them all together. The 3 and 3 cancel out. 2 and 2 cancel out. This is 1 plus 4. Okay? But what does this mean from sort of a intuitive way is I have a linear combination that is 1, 2. This chain is 1, 2 plus 2, 3 plus 3, 4. Okay, so let me highlight it by yellow. This is my linear combination of edges. And at the end of operation, I say, what is the boundary of this edge, which is actually a path in this simplicial complex? It says, well, in this case, the boundary of it is vertex 1 plus vertex 4. Not surprising. I have a path, and it's going to tell me the beginning of the path and end of the path because those are on the boundary. And what's interesting, when you take this, any interior ones are canceled out because I have 2 copies of them, right? So that's what it is, okay? So you can take the boundary of a chain, but now I can take the boundary of the boundary. So now if I take the boundary of a boundary, what do I have? I still use the same example, which is the boundary of chain C, and I take the boundary of that. I know the boundary of the chain C is already 1 plus 4, so I'm taking the boundary of 1 plus 4. 1 plus 4 is a linear combination of vertices, and there's one thing I didn't tell you. If I have a vertex, the boundary of it is equal to 0. So in some sense that, a vertex don't really, it's sort of, there's not well-defined boundary. Well, the boundary is 0. So in this case, this is 0. Okay. So we're going to do more examples. Let's do one. So let me just, before we do more examples, let's talk about the fundamental lemma of homology. Is that every chain, I'm using D as a notation. It's not a perfect notation, but let's say my chain is a P plus 1 chain is denoted by D. Then we say that whenever you operate over the boundary operator twice, you're going to get 0. Okay. So of course, there is a dimension that I didn't tell you, is the boundary operator's dimension. So if my D is a P plus 1 chain, then the boundary operation is looking at the boundary of the P plus 1 chain. So the boundary operation is have a dimension of P plus 1. Okay. So, but let's for the time being ignore that notation here, but let's just look at what is the boundary of a triangle and what is the boundary of a triangle. Okay. So again, it's the same exact example. My 1 plus 2 plus 3. So 1, 2, 3 is an element in 2-dimensional chain because it's a linear combination of triangles. Now I'm going to take the boundary of it. The boundary of the triangle 1, 2, 3, remember I said it's going to be all its edges. So it's going to be 1, 2 plus 2, 3 plus 1, 3. Now I want to take the boundary of this result. So I'm taking the boundary twice, basically. So I can do it, right, this rotation. Then I'm going to take the boundary of the previous boundary, which is 1, 2 plus 2, 3 plus 1, 3. And this is equal to the boundary of 1, 2 plus the boundary of 2, 3 plus the boundary of 1, 3. And remember, the boundary of an edge is its vertices. So this is 1 plus 2 for the first boundary of the edge 1, 2. 2 plus 3 is a boundary of the edge 2, 3. And then 1, 3 is the boundary of the edge 1, 3. Now everything cancel out. This is equal to 0. Okay. So essentially what 0 means, it says the boundary of a chain is empty. Okay. All right. So let's put this all together, right? Again, feel free to interrupt me because there's tons of information here, and this is sort of a crash course over homology. Okay, so we can do more examples. For example, okay, let's do the same thing before. 1, 2, 3, 4. This is my simplicial complex. And let's say I have a particular chain. Let's call this chain to be a linear combination of edges. Again, I'm going to do this linear combination is 1, 2, plus 2, 3, plus 2, 4. Okay, so what is this? This is a linear combination of those 3 edges. So now I'm going to ask you, without actually doing the operation, don't do it algebraically, but just intuitively, can you tell me what is the boundary of this chain?
The vertices 1, 2, 3, and 4.
Yeah, right. You kind of just imagine what is a boundary, right? Okay. So, but if I do it algebraically, as I described before, I'm going to take if I take the boundary of this chain, I'm going to basically operate on each individual element. Okay. And when I take each individual element, I'm taking the boundary of each of the edge, which is the vertices on the boundary of the edge. Okay. And now, because 1 plus 1 is equal to 0 based on our Z2 coefficient, basically whenever I have 2 copies, I cancel them out. This is what I get. And this is exactly how I pictured. All right. Now let's do a little bit more complicated example. Let's say I have 2 triangles in the simplicial complex. And my chain is 1, 2, 3 plus 2, 3, 4. This is my linear combination of the triangles, okay? What is the boundary of my chain? Can someone tell me?
Is it 1, 2, 2, 4, 4, 3, 3, 1?
1, 2, 2, 4, 4, 3, and
3, 1. 1,
3, 1. Yeah. So this is correct because the boundary of those 2 triangles are the one I pictured in red. It's a boundary. All right. But how does this happen from an algebraic operation? In order to get here, I really compute the boundary of 1, 2, 3. Well, actually, let me just do it step by step. I'm going to take the boundary of 1, 2, 3 plus 2, 3, 4. This is boundary of 1, 2, 3 plus a boundary of 2, 3, 4. And boundary of 1, 2, 3 is also the edges, 1, 2 plus 2, 3 plus 1, 3. Boundary of 2, 3, 4 is 2, 3 plus 3, 4 plus 2, 4. And because the edge 2, 3 showed up twice, they canceled out, and that's what you get. Okay. Now let's do one more step. I want to take the boundary square of this. So I take the boundary of the boundary. Okay. So if I take the boundary of boundary, I'm taking the boundary of the previous boundary I just computed, which is 1, 2 plus 1, 3 plus 3, 4 plus 2, 4. Can someone tell me what do I get?
0.
0, right? 0 by the theorem I just said, but it's 0 also you can validate because the boundary of 1, 2 is 1 copy 1 plus 2 plus boundary of 1, 3 is 1 plus 3. The boundary of 3, 4 is 3 plus 4 plus the boundary of 2, 4 is 2 plus 4. There's exactly 2 copies of each. So they all canceled out, so that's 0. Okay. Why am I doing all this? Because remember, if I want to compute homology, I want to compute connect component, I want to compute tunnels, and so on. Those are fundamental operations when I'm computing homology. All right. So again, before I do that, I need to introduce a few more examples, a few more definitions. Homomorphism, okay? Homomorphism is a map between the groups that commutes with the group operation. If I have two groups, A and B, there's a map between them where each of them has some sort of operation. We're saying that this operation of AF operating on the operation from the first group is equal to if I apply them independently to the second group. So how do I make it precise? We only care about the boundary map. So let's say the boundary map is a homomorphism. Why? Because let's say I'm care about, let's say if P is equal to 2. So I'm talking about boundary map for two simplices. So sigma 2 is C2 to C1. What does this mean? This sigma, right now I put a dimension there, but sigma 2 is a boundary operator over linear combination of triangles. And what I just did is that if I do a linear combination of triangles, if I take this operation on here, I can then use the operation, I can split the operation into this form. This is precisely because my boundary operator is a homomorphism. Why? Because if I highlight this red operation here is the operation that is part of my two-dimensional chain group. But now this pink operation is the operation that is part of my one-dimensional chain group. Okay, so that's precisely this condition. So my boundary operator, let me just repeat it again. The boundary operator operate on some chain, in this case, 1, 2, 3, and 2, 3, 4, is equal to the boundary operator of each individual element So basically, this thing here corresponding to my red solid dot in my notation, and this operation here corresponding to my hollow dot in my definition. Okay. But this is just all mathematical formalism. All that is saying is that if I operate, like my boundary map satisfies this condition that if I apply a boundary over a linear combination, it's equal to applying a boundary to each individual element and add them together. And that's what it means. So now, once you have the chain group, you can connect all those chain group through those boundary maps, okay? And that's called a chain complex. For all our purposes for this lecture, I only care about linear combination up until triangle. So I'm just going to write it as the following: C2 to C1 to C0, okay? So I'm going from linear combination, a group that is linear combination of triangles, to a group that is linear combination of edges, to a group that is linear combination of vertices. And they are connected by boundary maps, okay? And if I really want to emphasize the dimension, the first boundary map operates over linear combination of two simplices, which is triangle. So I'm going to put a 2 here. The second boundary map operates on linear combination of edges, which are one-dimensional simplex. So I put a 1 here. But that's just, in a lot of cases, I can ignore this, but with understanding that it's just taking the boundary, okay? This is called a chain complex because they are chain groups connected by the boundary operator, which by itself is a homomorphism. Okay. Chain complex. This is called a chain complex. It's called a complex because it's a sequence of those groups connected by maps. Okay. All right. Are people still with me? Okay, so this is pretty dense, and I will try to post some additional reading material. This is part of the textbook, right? If you go back to the textbook, there's a chapter on this. I will say it's a very dense chapter by itself because, like I said, it's pretty much a first chapter of algebraic topology book. But all that is saying is that I can operate over linear combination of triangles, linear combination of edges, linear combination of vertices through those boundary operations. So now the next concept is called a p-cycle. Okay, so a p-cycle is a p-chain with empty boundary. Okay, so let me replace p by 1. So a 1 cycle is a 1 chain with empty boundary. So hopefully it will give you an intuitive idea. So let's say right now, if my chain is 2, 3 plus 2, 2, 4 plus 2, 3 plus 3, 4, what is that? It's 2, 4 plus 2, 3 plus 3, 4. This is a linear combination of those 3 edges. And I say it's a 1 cycle. Remember the English definition of a cycle. It starts from some origin and come back to itself. That's the definition of a cycle, okay? Here, the definition of a cycle from the algebraic operation is to say if I take the boundary, if the boundary is 0, it's a cycle. Why? Because the beginning and end is the same, which means they appear twice, which means all vertices in my in this chain is visited twice. So it's 0 boundary, and it has a 0 boundary, so it's a cycle. Okay. So how do we check that? We'll say is my current one 2, 4 plus 2, 3 plus 3, 4, is it a cycle? I'm taking the boundary of it. All right. The boundary of 2, 4 is 2 plus 4. Boundary of 2, 3 is 2 plus 3. Boundary of 3, 4 is 3 plus 4. And you know that each one of them appear twice. This is 0. So it's a cycle. Okay. Why is it related to homology? Right. In this particular case, if you look at this particular cycle, it's a loop. It's a tunnel in my space. Okay. Well, of course, not all cycles corresponding to the actual homology. So let's give another example of a cycle. Okay. So let's say if my chain is equal to 1, 3 plus 3, 4 plus 2, 4 plus 3, 4 plus 1, 3. Is this a cycle? Any volunteer?
I think it's not because 2 of the edges direction is inversed.
No, we don't care about direction right now. The direction doesn't matter.
So the value is coming to 0. So by definition, it's a cycle.
Yeah, by definition, right? So folks, remember right now, I don't care about direction. If I do care about direction, then something else has to happen. But here, if I take the boundary of it, it's 1 plus 2 plus 2 plus 4 plus 3 plus 4 plus 1 plus 3. So every single vertex showed up twice. So that's 0. So this is a cycle. Okay. Let's do one more. C prime is equal to 1, 2 plus 2, 3 plus 1, 3. Is this a cycle?
Yeah.
Yeah.
Okay, right? Again, because if I take the boundary is equal to 0, because every single vertex showed up twice. Okay, now you know the cycle. The cycle, all the collection of one-dimensional cycle is what we call a subgroup of the chain group. Okay, so it's a subgroup because they are all the one chain, but with an additional constraint. Right, remember the one-dimensional chain group C1 is all the linear combination of edges. The cycle, which unfortunately I'm using this Z, not the other, double bar Z. This is single Z. This is a notation for a subgroup in C. So when you say a subgroup, it means that okay, the element in this group is still element from the bigger group, but it has constraints, so it's smaller. And what is a constraint? Is that all the ones that form the cycle group, right? A group of, say, one cycle, there's the one chain with empty boundary. Okay, so in some sense, there is a subset that satisfies the same condition. That is a subset of C1, but it's by itself is a group. Okay. And then there is this notation to say it's a kernel of the boundary map, meaning that what is a kernel of a map? A kernel of a map is everything that takes it to 0. So, and you're going to see a picture soon. Hopefully, that will make it make it clear. So, Z0 is a kernel of sigma 0, which is equal to C0. This is sort of like a additional condition I want to do. And then, of course, like say -1 chain is by default 0. And that's just going to here if I want to extend it in certain cases. But really, we're talking about a subgroup of the chain group, which are the chains who has 0 boundary. And that's called a cycle group. And now I need to define one more definition. A P boundary is a P chain that is a boundary of a P plus 1 chain. So that means that C is part of the boundary group if it is a boundary of some higher order simplices, or higher order chains, okay? So when I say it's a boundary, it means it bounds something versus bounds nothing. So again, this is going pretty fast, so feel free to stop me if you need some time to digest. So for example, a 1 boundary is a 1 chain that is a boundary of a 2 chain, okay? How do I decide on that? So if I have a chain, in this case, if my chain is equal to 1, 2 plus 2, 3 plus 1, 3, I say this is part of this is a boundary of a 2 chain, right? This is a 1 chain, but I say this is a boundary of 2 chain because this is equal to the boundary of the triangle 1, 2, 3, right? We know the boundary of a triangle 1, 2, 3 is 1, 2 plus 2, 3 plus 1, 3. So this is a boundary of this triangle. So it's part of it's a P boundary. So in this case, it's a 1 boundary. Okay, so C is a 1 boundary. When I say it's a boundary, it just means it bounds something. It bounds this triangle. Okay. Now, if I have another example, C prime is equal to 2, 3 plus 3, 4 plus 2, 4. And what it is, that is 2, 3 plus 3, 4 plus 2, 4. Okay. But I'm saying that this is not a 1 boundary because there does not exist a triangle that this is a boundary of. Does that make sense?
Yeah.
Yeah, it's quite a bit of a thing. Is that okay? So it has to be, first of all, a 1 boundary. It has to be a 1 chain, but then I put additional constraint on it. It has to be a boundary of some 2 chain. So it has to bound some triangle or linear combination of triangles. All right. So let's do one more example. Let's say this is my simplicial complex that contains 2 triangles, okay? And I'm going to ask you, I have a linear combination of edges, 1, 3 plus 3, 4 plus 2, 4 plus 1, 2, okay? Let me highlight it. This is my 1 chain, okay? Now my question is C a 1 boundary? Does it bound a linear combination of triangles? The answer is
Yes.
why?
It is a boundary of the 2 triangles.
Yes. So it's a boundary of a linear combination of 1, 2, 3 plus 2, 3, 4. Okay. But of course, I can do this. If I have C prime is 1, 3 plus 3, 4 plus 2, 3. Okay. Is this a one boundary?
No,
Why?
it cannot be represented by a common boundary of two triangles. I guess I
Exactly.
have to
There's
say.
no two chain that this is a boundary of. That's what it means. Okay. So now we know that whenever I talk about P boundary, they are P chain that satisfy certain condition. So they are again subgroups, but then they are the image of the boundary map. So what is an image, right? An image is take everything in the domain and look at what is mapped to. That is the image of the map. Again, this will come clear very soon. This is really the big picture we have. Okay, and this is the picture where we talk about the homology groups. And again, this is a lot to absorb in one single. Oh, I have a question mark here. This should be the textbook that we have for this class. We have sort of a group operation, and those groups are connected by boundaries. Okay, and the piece homology group is everything. This is what's called a modular or a quotient map. So this is saying that the piece homology is the piece cycle group modular the piece boundary group. Okay, so this is a lot to absorb. So if this is the first time you've ever seen this, don't panic yet, because we're going to dive into it. And we're going to dive into it to look at examples. So let me just do it over. This is my two-dimensional chain group, one-dimensional chain group, zero-dimensional chain group. And you know they are connected by boundary maps. And I'm going to ignore the dimension on the notation. So you know that it's boundary. So what did this do? This thing here, if I have an element, in here, it's going to map to an element in here, right? What is the example again? 1, 2, 3, 4. If I have an element that is 1, 2, 3, which is a triangle, right? It's a linear combination of triangle. If I take the boundary, I get a linear combination of edges. So what is the boundary of 1, 2, 3? It's an element that is 1, 2 plus 2, 3 plus 1, 3. And you know, any element in here that is a one-dimensional chain, if I take the boundary, it's going to go to the element that is linear combination of vertices. So let's say if I have edge 1, 2 in here, I will map to 1 plus 2, right? So this is how the map's going, right? And of course, what is the 1, 2 plus 2, 3 plus 1, 3? This will map it to 0. Okay, right? Because the linear combination of all of them canceled out. So this is how the maps are happening between groups, right? You know the element from a chain, two-dimensional chain group mapped to an element to a one-dimensional chain group mapped to an element in a zero-dimensional chain group. Okay, so now I have introduced the other two groups. Those are the groups that is Z. The notation of Z means that it's the cycle group, and the notation B means it's a boundary group. Okay, so how do I add to it? I have, again, these three groups. I'm just going to do it larger. And we say that those groups are subgroups, and then their inclusion relation is by different sides of the circle. So if you see here, this is Z2 and this is B2. So what does that mean? Z2 is the 2 chain which has 0 boundary. And B2 is the 2 chain who is a boundary of some 3 chain, okay? And I'm just going to draw them first, and then let's give examples. Oh. So remember, there is a notation that B is an image of a boundary and Z is a kernel of the boundary. So let's look at Z1. Z1 is a kernel of this boundary map. And B1 is an image of this map. Okay, so that's why this picture is looking like this, is because B1 is an image of it. So this whole picture of going from the big C2 to B1 is because I take every element in Z2 and map it to B1, because B1 is an image of this map, right? It's all the possible things in the code domain that is mapped, from the input to the output. So same thing with B0.
Did you say B2 or sorry, did you say Z2 or C2?
Oh, no, B1 is an image of this boundary map. And B0 is also the image of this boundary map. Let me put a dimension here. B1 is an image of a boundary map in 2 dimensions. Yeah. B0 is a boundary map of 1 dimension, right? Because remember, they are in the boundary group because they are the image of some high dimensional chain. Does this answer your question? Or maybe you can state your question one more time.
I think that answers my question.
Okay, good.
So like, it's the image of whatever would bound in the C2. I guess I'm also not really understanding, or I'm kind of understanding like the graphical, how you're representing it.
Yeah,
between the circles.
Right. So let's put it this way. Let me even do a very naive version. Let's say I have a function f. Okay, my function f goes from 1, 2, 3, 4. This is my domain, and I map it to some integer. Okay, so let me even better. Let me say my function f is from set A to set Z. What is my set A? My set A is just 4 integers. 1, 2, 3, 4. My set Z is all the integers. Okay, all the integers. So Z is an infinite set. Right. And my function is fx is equal to 2x. All right. So what do I want to do is I say, okay, I'm going to do this sort of, this is really the diagram for this function. Okay, so this is my set A, this is my set Z. My set Z is all the integers, my set A is just 4 integers. Okay, so 1, 2, 3, 4. So, and then this is my map F. Okay, now if I want to say what is the image of this function, so what is f of A? So by definition, what is my f of A? It's going to be a set, right?
Mm-hmm.
So what is in my f of A?
Two.
It's just going to be all of A individually multiplied by 2.
Exactly.
But it's going to be the same size.
2, 4, 6, 8, but it's 2, 4, 6, 8, okay?
Mm-hmm.
But the way I'm going to draw it, I'm just going to draw it like this. This is 2, 4, 6, 8, and I'm going to draw it like this. In fact, let me draw it a little bit better. I really want this to touch the bottom. Okay,
Okay, so the actual size of the set isn't changing. It's just representing that it's a part of
Well,
the larger set.
right, but it's also possible that two things map to the same thing. If they both have zero boundary, for example, they both map to zero. The size, it's this notation. I'm going from, say, the orange circle to the green circle together with this particular line right here. This is just saying that I am going to map the entire set A to its image. So this orange set is my set A, right? And my green set is the image of my function. That's what I mean.
Okay.
So going
Gotcha.
back to this notation, by definition, B1 is an image of this function C2 or sigma 2, right? This boundary operator 2 is just to say I'm taking all the orange, well, all the orange set. I look at what is in the image of this function, right? And then this function is now this with this particular line, right?
Mm-hmm.
The same thing, I have this line, I map everything in my C1. This is just more of a visualization of how you understand. I take everything, all the elements in here, and then there I'm going to look at the image of it, and then it's going to be in here. That's what it means, okay? So by definition, because B1 is an image of sigma 2, I'm going to draw it like this. By definition, B0 is image of sigma 1, so I draw it like this, right? But now, remember I said Z1 is a kernel of sigma 1. So what is a kernel? Kernel means that it's everything in the domain of sigma 1 that map to 0. So that's why you see this picture here. That's why you see this picture here. Oops. It's everything that map to 0. So what's happening is everything in Z2 map to, is everything in Z1 map to 0, and everything in Z2 map to 0 through the boundary map. Okay, so that's what the second line means. So again, I'm talking about here. Okay, and again, I have to warn you, this is all very abstract, but it's not too hard to understand what is the different elements in here. Okay, so let's give a few examples and then we'll actually run out of time, but we'll continue next class. If I start with, let's see, if I start with an element in C2, okay, what is in C2 in my example? The element in my two-dimensional chain is a linear combination of triangles. So let's say I have an element that is the triangle 1, 2, 3 that is in this group C2. But where it is exactly I need to see, right? So if I take the boundary of 1, 2, 3, it's become 1, 2 plus 2, 3 plus 1, 3. Okay, this is sigma 2. Okay, so that's the first thing. But now I want to ask, okay, is this a boundary of something? If it's a boundary of something, then it should be 0. Sorry, someone has a question?
No, I was just saying it on to me. Sorry.
Oh, that's okay. So if I have, so for sure, this is this is a boundary of something, right? So remember, everything that is in the boundary group has to be in the image of the previous one. So of course, this has to be, a one boundary is a one chain that is a boundary of two chain. Okay, so for sure, I'm going to put the element, let's call it C. Oh. I'm going to put this element here because the element 1, 2 plus 2, 3 plus 1, 3, this is a one chain, but it's also a boundary of a two chain, okay? So that's where I'm going to put this linear combination of one chain here. Does that make sense? What is the element in B0? Right? Remember, what is a zero-dimensional boundary? It's a boundary of one-dimensional chain. So for example, 1 plus 4 is in B0, okay? So what is 1 plus 4 in B0? It's the linear combination. It's a boundary of a one chain. So what this is a boundary of? This is a boundary of 1, 3 plus 3, 4. Right? But now, this is sort of my last statement, and we'll resume from here in the next lecture. The homology group, especially the one-dimensional homology group, by definition, is Z1 over B1. What does that mean? It really means that it's part of a boundary, it's part of a cycle group, but not in the boundary group. So actually, one-dimensional cycle is going to be the element in the yellow region.
It looks like it's frozen for me. Might just be me. There we go.
Okay, it's some delay. So what does this mean? Zero-dimensional homology, one-dimensional homology. Remember what is one-dimensional homology? One-dimensional homology are loops or tunnels, okay? If you just look at my example space on here on the left-hand side, there's one loop in here, right? There's one tunnel in here. So the one-dimensional homology group are the one chain which is not a boundary, okay? What is example? The one chain that is not a boundary is 2, 3 plus 3, 4 plus 2, 4, right? It's a one chain, but it's not a boundary because there's no triangle that it bounds. But if I put it in a picture, it's 2, 3 plus 3, 4 plus 2, 4. That's exactly corresponding to that particular tunnel that we care about. So the homology is picking out, in this case, one-dimensional homology is picking out the one-dimensional chain, which is a linear combination of edges, which are not boundary of linear combination of triangles. So if they're not boundary of linear combination of triangles, that means there's a tunnel right there, and that's my one-dimensional homology group, okay? I'm going to end my lecture here, and I'm going to start streaming, and then folks can ask questions. And this is a very dense lecture, so we're going to revisit some of the questions again in the next lecture as well. Okay.